exercises. Today we begin with a presentation by Paavo Pylkkanen. He is a professor at the University of Helsinki, Department of Philosophy. He specializes in philosophy of mind, philosophy of physics, and specifically on the law. Paavo?
Okay, thank you very much. I specified the title just a little, so as you know, there are many different approaches to try to explain consciousness in terms of information. IIT, David Chalmers, Global Workspace, others, but I've been focusing on something which is probably not so familiar to you, which is using this quantum information. And of course, in this approach, it's a little difficult, like in a meeting like this, there won't be too much focus on quantum mechanical approaches. It's a little bit like a French approach. The most well-known is, of course, Penrose and Hameroff. So I think what I'll do today is to focus a little bit like a tutorial in the beginning, just so what you will actually hope to experience. So this is your bonus for coming so early. So as the time was so short, what I'll try is that you will, after this, like roughly half an hour, you feel you will understand quantum mechanics better than you did before. For those of you who already understand quantum mechanics, I apologize, because then you'll probably be bored, but let's see what happens. What I will also mention briefly is about the new fundamental notion of active information, which the physicist David Bohm suggests would actually apply even at quantum level, but other levels. And finally, we'll get a glimpse of how active information might explain our knowledge of qualia and consciousness. This is actually from a colleague, Ron Chrisley, who's one of the few people who have looked at these approaches. And maybe in some ways, I think my talk would be a kind of counterfoil, let's say, to illusionism or this whole idea that consciousness might exist. I think my general point would be that often people who think we can explain consciousness, let's get rid of it, they still presuppose a fairly traditional view of the physical world. But of course, then the scientific approach would have to look into quantum theory relativity for a general view. And this is in a way what I would say that in consciousness studies we need a scientific metaphysics. And what I mean by that is a general framework that is implied by our best theories of physics, quantum theory of relativity, and the special sciences. So, and that doesn't mean that consciousness therefore is reduced to quantum mechanics or anything like that. But I think we have to get our framework right. Otherwise, our discussion about consciousness is exactly the same that it would have been in the 1800s, or whenever classical physics was ready. And so let's see what we might get here. So in some ways, I just want to introduce some, if you like, new ideas in physics, and then see what sort of how we might be able to make use of them. And of course, we've been writing about this quite a bit. And so yes, okay, let's go. Now, I would suggest a good candidate for this kind of general framework would be Bohm and Hardy's implicate order program. The implicate order is something they actually developed already in the 1960s with Penrose. The idea there is that quantum features such as no locality imply that we cannot no longer think that space-time is fundamental, and the only relations in physics are not spatial relations between material objects and space-time. Actually, what we need to combine with general relativity quantum mechanics is a deeper level, something that John Wheeler called the pre-space, Bohm and Hardy called the implicate order, and actually in June, they started a new program, an ERC synergy grant, like 10 million euros, where it's called Universe Plus, where people have roughly the same kind of approach. They're trying to look at the deeper level in physics, and out of which then space-time will be emergent, material object will be emergent. And hopefully you might get, like quantum mechanics, general relativity as special cases. Whereas if you just try to put them together, you get serious contradictions. But I'm not going to talk about that so much. I just say let's keep it in mind that the Cartesian res extensa explicate order is not all there is. There may also be something you might call the implicate order with properties like non-locality. And maybe there's a sense in which Descartes was right. Because by saying that consciousness doesn't live in res extensa, who knows? I mean, maybe he was right. What he was maybe wrong was to say that matter can be identified with res extensa. But anyway, I just leave that as a comment that actually Descartes may not be so bad as we are often told in every philosophy of mind textbook. Okay, but I'm going to focus on something much more concrete and simple, which is known as the pilot wave or ontological implication of quantum mechanics, where we get the new notion of so-called active information, and this is something like Bohm suggested already in the 80s. I was spending months in the UK interacting with him. I did my PhD on this topic, so I've been going on working on these ideas from for a long time. But the proposal there is that we could use this new information quantum mechanics for things like mental causation, perhaps even for consciousness. Okay, but to do that, I just anticipating that people aren't familiar, instead of just going to the nitty-gritty, I'll do a very simple reminder tutorial about quantum mechanics. And the nice way to do it, in the old days we always did that with a two-slit experiment, which is a very visual thing. And so I'm just going to tell you how three aspects: ordinary classical waves, ordinary particles, and then quantum objects. We have to wait for the third part when it gets perhaps really exciting. Okay, classical waves. So you see, if you put classical waves like water waves, it could be light waves, through a slit that's much larger than the wavelength, nothing very dramatic happens. However, if this slit or hole is, it should be smaller, right? I made a mistake there. So if you propagation of waves through a slit much smaller than the wavelength, you will get actually this kind of diffraction. So the wave will bend. And then when you put two slits together, you have two waves with diffraction, and when they meet, they will interfere. So at some points they will make each other stronger when they're in the same phase, and if they are not in the same phase in a certain way, they will cancel each other out. And so this is actually a photograph of water waves in two slits, so waves that up in some directions and they cancel out in other directions, okay? Hopefully familiar to most of you. But if not, here, this is the basic features of wave motion. And you see more schematically what happens with waves is then that we get these interference fringes or patterns in the screen, and some areas where you get a lot of waves and others where you get nothing at all. So interestingly, even if you put two light beams together, you will get darkness if the phases are different in a suitable way. Okay. And then when we have those stripes, many stripes there, that is called interference pattern, interference fringes. And for a physicist, interference is a signature of a wave. It's telling them the wave was here when they see something like that in any experiment. Okay. All right. Moving on, let's just take ordinary particles. This is where usually everybody is with me. Students and philosophy students understand this much, so this is not the difficult part. So if you shooting two bullets through these two holes or slits, you will get two stripes there. You can try it if you don't believe, but I guess most of you would agree that there's nothing very crazy about this. And so now we get to the quantum objects, for example, electrons, and we can ask what happens if we pass electrons through the two slits. And the electron was initially assumed to be a particle. It has mass and charge. This would be measured. So physicists thought, well, they must be like little bullets. I mean, and the Newtonian mechanics was what there was. So this was the way physicists expected the electrons to behave if you put them into this kind of situation. But actually, this is what the experiment shows. So you get those many stripes, and so I won't go into all the details, but just notice that. And we would ask, well, why do the electrons one by one form a pattern of many stripes rather than just two, right? Why? And you see, if you look at this, well, it's a wave pattern that we get there. So there's something wave-like going on here. And we can say that they actually form an interference pattern. And we even get that pattern if the electrons enter the slit system one by one. And here's a picture of an actual experiment. So I guess in the A, there's just like 10 of them, and then more and further. When they keep going one by one, you can see the pattern, and here you can see it very dramatically. So this is very crazy. Like, it's almost like, imagine I make two holes in the table, and I start dropping sugar. I expect to get two piles. This is what physicists thought to do. But with the electrons, I need many piles of sugar. So here's magic. So it's not just the magic of consciousness, it's the magic of quantum mechanics here. And this is, of course, before Feynman thought also way you can ever understand what's going on here. And you see, I won't go into it, but one of the, you might say, well, let's see what happens, but there's the uncertainty principle, which prevents us from actually observing the little thingies. And therefore, it's not as easy to solve as one might think. Now, this is known, of course, as a wave particle duality, so the individual system exhibits both particle properties. As we saw, it arrives at the detector like the photographic plane at the single spot, like any good particle would do, right? But also there are these wave properties, because the place where the spot appears is constrained by the mathematics of wave behavior. It's got, instead of just making two clouds, somehow it's a mathematics of wave that tells you, you can calculate this pattern, and so each individual has to have a wave property. How would it else know to obey, select one of the allowed places in the interference pattern, rather than be, if it was good old Newtonian particle, there would be just two areas. Okay? And you see, there's still no commonly accepted way to explain the two-slit experiment for, let's say, for electrons. I mean, this is hundreds. I think 26 is going to be 100 years from the Schrödinger equation, for example. And of course, I mean, you may know there are all this number of interpretations. There's the good old Copenhagen view. There are pilot waves. There's the many worlds, spontaneous collapse, cubism, actually many more. If you go to Wikipedia, then you can really inform yourself of all the interpretations and their properties. And of course, in my half an hour, we can go through all of them. So we look at one of them, and why? Well, it does provide an explanation. Each interpretation has its problems, so does this one, but it has some advantages. And as a bonus, we might get even something relevant to understanding mind and consciousness. So let's go for it. So one of the interpretations, this de Broglie, it was actually invented by Louis de Broglie in the 20s, independently rediscovered by David Bohm, who made it more consistent. And you see, in here you actually say, well, the electron is a little particle. You're assuming that, but it's always accompanied by a new type of quantum field which guides it. This is why it's called a pilot wave. You see, the electron will go into one of those holes, but the pilot wave goes through both, and there's interference. So the wave patterns after the interference will be different whether or not one or two slits are open, and then the electrons will also be guided to obey this wave pattern. So for example, where the pilot wave has zero amplitude, the electron is not allowed to go there. So we have kind of an explanation here. And this is pilot wave, Bohm and Heine call it also the ontological interpretation, because it's trying to tell us what an electron is. And the way this works is that one just assumes that an electron is a particle which has a well-defined position and momentum at any given time. and it's accompanied and guided by a field sign which satisfies the Schrödinger equation. So in that sense, this is like ordinary quantum mechanics. We're not starting with a new equation or anything like that. We're using the Schrödinger equation, but what de Broglie and Bohm discovered is that you can actually construct a model by doing certain kinds of things. And just for, if you read popular quantum mechanics, this slide is for you. So in this model, it's not particle or field, which you will learn in every almost human textbooks. It's not a field which collapses into a particle. There's no collapse of the wave function in this model. It's not a field which branches into many worlds, like people like Everett and David Wallace would say. It's a particle and field, or Bohm, as Bohm would like, in his holistic way, he would like to say. It's an inseparable union of a particle and field. Okay? And this is a slide made by Basil Heidi. Basil and I have collaborated since 1991. And from here, well, it's a little bit small here, but anyway, for those of you who are interested in the technical details, so the magic of the Bohm theory is that you write the wave function in the so-called polar form. R is the amplitude of the wave. S is the phase. You put it in the Schrödinger equation, you get two parts, but the real part gives you this kind of equation, which almost looks like classical physics with an extra term Q. So this is why it's called Hamilton-Jacobi equation. Is one way of doing classical mechanics, but the quantum is modified with Q, and it's this quantum potential that is the exotic thing here. And so a potential can be understood as a bit like a mountain. So here we are looking at these are the two slits, and the electrons are coming from those holes toward you. And they don't want to go here because the potential is very high, the mountain is very high, and you can see it in this picture, nobody goes there. They like to go into those trajectories where it's nice and you can be lazy, you just move along. And surprise, surprise, we actually get here these interference patterns as a result of this. So these are possible trajectories for the particle, and a single particle will select one of them, depending on where it started over here. And where it started depends, there's a random process like a hot filament, which is the source of those particles. So just very quickly, this is why we say, well, in Bohm theory you can provide a nice visualization explanation of the greatest mystery of quantum mechanics, the two-slit experiment. Okay? But what Bohm himself later on got interested, when he got more interested in things like mind and consciousness, he also felt that, well, what's this strange potential? Because here you can see, we look at it in more detail, but you can see also in this picture that the R is the size of the wave, and it's both in the denominator and the numerator. The size cancels out. Here, size does not matter. So what does matter? It's only the second special derivative here, which is the curvature of this wave. The form, if you like. And from form we get into information. So we could argue that the pilot of interpretation implies some radically new ideas about the nature of these quantum mechanical processes. And something that Bohm himself emphasized, that it proposes that the new type of holistic active information plays a key role at the quantum level. Which then we could say this involves a radical change in what we mean by physics and the physical. Perhaps even opening up new ways of tackling the traditional matter problem. A lot of my work has been trying to spell this out. And you see, in particular, information can now be seen as a new fundamental category in physics. And this is not shadow information. It's not information for us. This is somehow information that is there completely independently of human beings. It's kind of a realist view of information. Information as objective commodity, doing things in the world, making things happen. Okay. And Bohm himself, proposed that this quantum information, this what we could call Bohmian quantum information, because there are other kinds of quantum information. It would connect the physical and mental domains as these have been traditionally conceived. Okay. And let's look at once more. I already showed a little bit, but here you can see it better. So you see with classical fields, like the electromagnetic field, the potential depends on the amplitude of the field. It's like, of course, like the brightness of the light waves. Or, if you think of a water wave, it's the size of the water wave that determines the effect the wave has on a floating object. But this quantum potential only depends on the form or shape of the field, not on its size or amplitude. And those of you with mathematics, you can see that it depends only on the second spatial derivative. So the situation here is, imagine you have your floating object, your rubber duck, in a very calm lake. And in classical physics, with classical waves, if you want to kick the duck or make it move, you have to make big waves. The bigger the waves, the more duck will move. In this situation, a very tiny wave can have a tremendous effect. So this quantum potential can be very large, as long as there are interference effects, or you have a kind of a form of the wave that will give rise to this large value, according to this simple equation. Okay? And so again, you see the idea, so this quantum field, and this is what Bohm started emphasizing, this quantum field is not pushing and pulling the particle mechanically, like a water wave would push and pull a floating object. Rather, the quantum field literally puts form into or informs the particle to behave in a certain way. Here we are going back, if you like, to the original notion of informare. And the energy, so what we're saying here is that the electron is moving under its own energy that is being informed by the form of this quantum field. And then there are various ideas where the energy would be coming from. But, of course, Bohm, he was a philosophical thinker. He was interested in not just the nitty-gritty, but these more general philosophical questions. And he suggested that what we see at the quantum level is actually an instance of a general feature of active information that we see operating at many levels of nature. And which is actually we have a lot of that even in common experience. And you see, so what's the basic idea? What's the naive idea here? Well, the idea is that the form that's carrying very little energy enters a greater energy, and as a result, the form of the greater energy becomes the same as that of the small energy, okay? And this is easiest to see in artificial devices. And this is an analogy, okay? So when we have a ship on autopilot, which is being guided by radar waves, those radar waves are not pushing and pulling the ship, okay? What's happening is that the form of the waves, which reflects the form of the environment, whether there's something at the bottom of the sea you should avoid or whatnot. This is taken up by the autopilot device and is used to direct the ship, okay? So this is a kind of an analogy. So, it's like the Bohmian electron is a bit like this sort of ship. And you see, and the analogy is here, you see this quantum field contains information about the environment of the particle. For example, the slits. And so, so you see the way this works in quantum mechanics is that to get your waveform, to get this wave, you have to solve the Schrödinger equation, but to solve the Schrödinger equation, you have to tell you what the situation is. So you have to tell it about the equation when one or two slits is open, and then the wave will reflect that. But of course, whether or not one or two slits is open is a fact about the macroscopic environment. So it looks here like the macro environment informs the tiny quantum object in some direct, immediate way. I'm not saying there's something interacting between the macroscopic slit. I mean, those can be centimeters, the slit but you can have it in your pocket. Just, the partition. And so this is something that I'll come back to a little bit later, that there's something in that sense very interesting here. And of course, some of you know in quantum mechanics, it's the relation of the macro and the micro. That's one of the key issues. Okay? And again, you see here, well, check, this is just to illustrate that if I do it here, we'll see. Oh yeah, sorry, I should have done it earlier. So for here you can again see that what I mean by saying that these things, these slits here can be macroscopic, and whether or not this one or two slits is open, it will then influence the Schrödinger equation and change the quantum potential. So that's just to repeat that point. Now, of course, you see, we've got many other examples of active information. I mean, of course, with computers, there's loads of information sitting there which can be activated. But then somebody say, oh, you're giving these artificial examples. I mean, come on, you know, the electron is not like that. But of course, when you go to biology, it's very common to say that things like the DNA molecule is a code, like a language. It informs protein construction. The DNA molecule is not like pushing and pulling, or the order there is not determined by forces of classical physics. It's something that can be used as a code, and that is again guiding protein construction. That's information for the cell. It's not information for us. So we have to get used to it, because I think one confusion about information, we always think it's for us. We're so selfish, right? But whenever I hear information, it's for me. No, the DNA carries information for the cell, but we don't have to be depressed about this, because there is information for us as well, right? For example, when you're reading a map in subjective experience, so you abstract the forms that in your mind that will give rise to, oh well, shall I go this way, that way? Especially important in Siena, because you know there's no straight line from the hotel to here. But then, of course, at some stage you will select one route, and that information becomes now active and is guiding you. The poor electron hasn't got too much choice. It has, wherever it happens to be, it will obey this information. But in the human mind, you actually get a richer set of possibilities. So, I mean, this is just to give you an idea that this active information, as such, is just part of our common experience. It's cool, but there's nothing very, if you like, crazy about it. Well, of course, when it does get exotic is when we try to extend it to the quantum level, like Bondi. And it could use the whole thing here is that this might actually have philosophical significance to our notions of matter, and including minor matter. And you see, well, again, to say that, I mean, this is how Bowman, they already wrote about this in the 83 article, and they themselves acknowledge that this notion of a particle responding actively to information in the quantum field is far more subtle and dynamic than any others that have either been supposed to be fundamental in physics. And this is one of course, this may be one of the reasons that still in the physics community, physicists find these kind of ideas difficult. There is a version of this Bohm's theory, which is called Bohmian mechanics, where they kind of made a very sober version. So, because you see, people who are very who only want to see matter, who want to almost go back to Newtonian mechanics or whatnot, they might like the Bohm theory. And of course, then when Bohm himself starts talking about exotic things like active information, then they don't like that. So if you like, David Bohm is the worst heretic in Bohmian mechanics. Just for those of you, if you start reading this stuff, you will know, you won't find much discussion of this. But from the philosophical point of view, I think this is the exciting part of the Bohm theory. I mean, the other stuff is okay too, but it's kind of maybe a lead too sober for my taste. Okay. Here's just for those of you who worry about the channel information. So with channel information, the idea typically is it's the measure in which a state of system is uncertain to us. So if you like, the more surprise we get when we get the information, the more information there was. Okay? Whereas here, Bohm claimed that active information is not essentially related to our knowledge or lack of it, because this information that's relevant to determining the movement of the electron itself, it's information for the electron, or as the philosopher Gretzky would say, it's information as an objective commodity. Okay, so and anyway, I mean, it's interestingly, those of you who know the integrated information theory of Tononi, will notice that there could be kind of similarity between IIT, or integrated information, and this Bohmian information. In some ways, there are also differences, but we discussed this with Tonoli in recent years, and I hope to write more about that in the future. But okay, but before I conclude, let me just say that, you see, there is the question, well, how might this then be relevant to understanding mind or consciousness? And you see, one possibility, if we do so-called quantum brain theory in this model, of course, then what we say is that the little thingies in our brains are not just particles, but in some circumstances, they might have actually this Bohmian pilot wave alive and kicking, and anything that can influence the pilot wave can influence particles, and it can be amplified to action potentials, and so on and so forth. And of course, a lot of people like Penrose and Hameroff have tried to argue that in microtubules in the brain, you could have this quantum coherent states. And of course, then you can apply this thing there. In my view, this is why I think this Bohm's information view is a better quantum approach than Penrose-Hameroff is, because I think the notion of information can easily be connected to mental states. Or, the brain is processing information, but also then, and from information we can then discuss whether, various mechanisms whereby information could become conscious. And so this is, I'll show you some articles, if you're interested in this, we'll be writing about this. I focus more on the physics part, because in some ways I feel if you don't understand the physics part, you're not going to read anything else either, because you just think, oh, it's just something. So this was my strategy for today. But I do mention, one of the philosophers that I've interacted actually since late 1980s is Ron Presley. He's a cognitive scientist philosopher at the University of Sussex. And he's been looking at this thing already 30 years or more. And he actually did he did a paper on quantum neural networks. We were discussing these things in 19, so this was one of the first ones, maybe published in 96, using the active information, the quantum potential in that context. But then Ron was also, he wrote criticism of the work that the Bohm, Heil, and myself are doing. One thing he was saying that if we want to say that active information is relevant to mental states and this kind of quantum active information. So Ron felt, well, and I was trying to suggest we might have sort of proto-intentionality here, it's a directness. Ron was saying, well, to have intentionality, there's got to be error. And then I said, well, okay, how can we have an error here? Maybe there would be a way of fooling the electron that two slits are open when there's not. So, some evil demon modulates this quantum field, and so the electron will misbehave, if you like, on the basis of misinformation. But I guess we left it at that, because this is kind of, at some stage you feel, well, what can we say about these things? But we had this meeting in Physics and Reality in Helsinki in early June. Ron was there, and he kind of went back to our own discussions. But he came up with this new idea. Because Ron has, of course, he interacted with Dan Dennett and for example, has ideas about qualia. Of course, what people want to do is to find qualia, get rid of qualia because we can't explain them. But now, Ron, maybe, he's getting wiser as he's getting older, who knows. He actually, let's turn it the other way around. And this is his proposal. This is quoting from his slide in Helsinki. What he was saying is that if our knowledge of our own qualia is somehow, by virtue of being informed by active information, then we could explain the actual immediacy, intrinsicness, and privacy of qualia. And Ron has argued elsewhere that ineffability follows from privacy. So, for example, immediacy. Knowledge of qualia is not mediated. It is not by virtue of contingently interacting with something else that the particle is informed by the quantum potential. And so the inability to find misrepresentation here is a feature, not about. Immediacy yields incorrigibility. And a particular note is that the particle can be directly informed about high-level complex classical features, namely the presence and location of slits. These things I tried to emphasize a little bit earlier on, how this works here. But somehow this idea is that, you see, you could have, what do we need for this? Why would we need any, okay, you can have as much as quantum information in your brain, but what does it do? As opposed to, let's say, classical or any other kinds of processes. And the idea here is to try to make use of the kind of immediate quality that seems to be there. And of course, I mean, this is, again, it's not just for, there could be implications here. You see, the properties of quantum mechanical information might help to understand our immediate access to our own consciousness. And of course, we know from Descartes that we cannot be wrong about the sentence, I think I exist, when we think of it. So there's this whole idea of incorrigibility in the first person perspective that's kind of built into our tradition. And so I already mentioned that quantum mechanics might say Descartes in the sense that maybe Descartes was correct about consciousness. Not everything needs to live in space-time. I mean, consciousness is more like what Bohm would call it, the implicate order. And I've written about that in my book. But of course but it's not just ontology. Here, actually, the way Ron is proposing now, it might have radical implications to epistemology as well. So we'll see where we get with this. Maybe we thought we might make a joint paper or something like that, but waiting for that, here are some old ones. So anyway, thank you very much.
Yeah, thanks a lot for your talk. I would like to ask you whether you could be a bit more specific how these fascinating facts you told us are relevant for a better understanding of consciousness. So, I mean, so my worries result from the fact that what seems to be problematic is not so much that the brain is able to process information. I mean, we now have deep convolutional network which map pretty much what goes on in the visual cortex or in the ventral stream of the visual cortex. So that doesn't seem, and we have even models that simulate processing in the language areas of the brain. So the modeling and understanding of information processing doesn't seem to be so problematic. What seems to be problematic, how do we, if we use the concept of consciousness, which in my view is a bit problematic as well, but let's set this aside, how does this information processing in specific conditions become conscious? Or how are we able to be aware of this under specific conditions? So what would your theory contribute to that question?
Yeah, right. That's a good question. I think, of course, you still say that a lot of things that are happening in the brain are macroscopic and classical, and that's what we need to communicate even now. But of course, the feature with the curious feature of quantum mechanics is that there is this, if you like, another level of these quantum objects where there's kind of different dynamics with different properties, things like entanglement or non-locality and certain holistic features as well. And you see, this is of course why people have been tempted to somehow, because a lot of people argue that they find this same a certain kind of unity, for example, in conscious experience, which people who study quantum mechanics, they get the intuition that this might be better explained with these things like quantum entanglement. And of course, then the question is that then we're proposing that in the brain there are, if you like, two levels. There's the level of classical information processing, classical thinking, if you like, but then there would be this deeper level of processing. And we don't have a good, commonly, even among the people in quantum consciousness, there is no commonly accepted view. What is it that makes information consciousness, or how does consciousness arise in this picture? So the hard problem is there, but in this small picture there are a couple of models. One could use any of these theories we have, use integrated information, Loris Albantekis and others, they made, I think Zanardi, they made a quantum version of IIT. There is the physicist Jack Sarfati, who works all kinds of wild ideas, but he has also suggested here that consciousness arises, if you like, when these so-called macroscopic fields in the brain act back toward this quantum field. So qualia would be like excitations in this Bohmian quantum field. And the idea here is that this quantum field is intrinsically mental, as opposed to other properties. And Bohm himself, he was favoring kind of a higher order theory. So I think there are all these possibilities, but we don't have a final answer. And I guess I've tried to explain this in more detail in some of the articles, like the ones I have on I showed in the last.
So if you want to let everybody ask their questions,
then I have some short answers. Difficult question, so.
This is similar to the previous question. First of all, I'd like to know what your reaction, what is about the objection that comes from the famous Bell's theorem against Bohm and the hidden variables, etc.
Can I take that first? Can I take it first?
But the very important question for me as a philosopher of mind is that this active information is valid for all macro phenomena that are informed by micro phenomena. I wonder whether there's a particular form of this process that is valid only for consciousness. Perose and others said maybe in the microtubules of the cell, but the objection by Church and the others was, well, but this theory is at too low level of analysis. We have to understand what consciousness seems to be a higher order property of dynamics.
Yeah, well, the first question about Bell inequalities, it was actually the Bohm theory which inspired John Bell to make his theory. You see, the Bohm theory is non-local. I didn't go into all that, but this is one of the features what makes also the active information an exotic feature. And Bell's question is, well, are all hidden variables, do they have to be non-local? Okay. And with all the experiments being done, it suggests yes, that is so. So the Bohm theory predicts the same results of the standard quantum mechanics, but it makes non-locality more explicit. And about the other idea of this, about this specific, if there's something special here and whether this is too low. Of course, in the case of Penrose and Hameroff, they think that consciousness arises with this collapse of the wave function taking place in neural microtubules as a result of gravity. Gravity being very weak force, but still and Penrose feels that because this is a process that goes beyond computability, I think he sees this as a place where consciousness might come into an otherwise mechanical, deterministic, if you like, illusionist universe, just running through good old Newtonian spirit. And in the case of the Bohm thing, with this idea of information, we could interpret the Penrose-Hameroff theory in terms of this active information, where we would have both incomputability with Penrose idea of intelligence, and then some mechanism which makes the non-conscious information conscious, but we don't have that mechanism in the end.
My name is Alba Bernardini. I am a teacher, first of all. Then I am psychology and philosophy. I follow your presentation, and I make this observation. The active the active information of the quantum is given by physical energy. I am also teacher of physical education. And also I have to make another observation. Computers have no three-dimensional information, while the body is three-dimensional information. It is able to give information necessary to elaborate external and internal energy. In this way, the dualism mind and body is not true, because they are unit or joined by energy.
Please ask a question.
The question is observation.
Given that there was no question, there is no need to answer. We have the last question in Zoom chat. According to the path of interpretation, is going on to introduce a measuring device consisting of the double slit experiment, and particles go back to behave classically, not showing any more than the interference part.
Yeah, that's a good question. And remember, I told you that when you solve a certain equation, you have to tell it what is the overall situation. These are called the boundary conditions. And if you bring in any physical thing to the situation, which would measure like from which slit the particle goes through, you have to put that into your boundary conditions, and then when you solve your equation, the wave will be different, and from that, when you calculate the quantum potential from the wave, you will not get the interference boundary. So, in a way, the quantum potential provides a nice illustration also the way the holistic nature of any quantum mechanical situation.
So, thank you, Paavo, for your wonderful presentation.
Thank you.
We need to change our program. I'm informed that Leah Mudrik is online and she is able to present now. We will connect her on Zoom. Leah Mudrik is at